Okay, so this is a series circuit, and I'll put it over here. Sound of music. All right. 1 ohm, 2 ohm, 5 ohms. Is that what it is? 24 volts. Oh, A2. A2 is in here. All right. So here's the joke. Here's the joke.
Does it matter if the V2 is on the other side of the A2?
Doesn't matter. Doesn't really matter. On there, it's okay. So we'll hook it up the same way. We'll kind of go. Okay. There you go. Okay. So here's the joke. Here's the joke, because the series circuits and parallel circuits are sort of like these diametrically opposing things. Okay. In a series circuit, there is only one current, and the current encounters the resistors in a series, like the World Series. Okay. It's like it runs into this one. Okay, because this current is going clockwise around here. This is the positive side, there's the negative side, and the current is going this way, like this, and that is the one current. Whenever it is measured, since charge is conserved, okay, and since charge is not going to spray off this wire, we don't have a high enough voltage where it can like charge the air molecules and fly off into the air like the Van de Graaff did. So since it's going to stay on this wire, if, for example, 5 coulombs per second is passing this point, it's also passing this point and this point and this point and this point and this point. There's only one current, and whenever you measure a current in this circuit, you will always have the same current. Because if you had like 5 coulombs a second passing this point and only 3 coulombs per second passing this point, you would say to yourself, where are the other 2 coulombs per second going? There are no divergences. There's no other path for the current to take. Where is it? Right? Charge is conserved. It cannot just go away. So it's either going someplace else or it's being stored, but none of these things are storing charge. So there we have it, right? Okay. Does that make sense? So it's conserved. It's got a, there it is, right? So the joke goes like this. What's the difference between America and France? Besides like the language and everything, right? What's the joke, right? And the joke is that in France there are 1,000 kinds of cheese, but one religion. And then in America there's one kind of cheese. Actually, there's 2. There's white and yellow, right? Okay. And 1,000 different religions. Is that right? That's what it is. And it really is true. I mean, it's like it's like in France, the school kids have Catholic holidays off. Like, yeah, all of them. It's like this is why they're generally having problems with immigrants and stuff like that. But anyway, okay. So in a parallel circuit. In a parallel circuit, it's the other way around. There's just one voltage, and then there's many, many kinds of currents, many different currents. So current is the thing in a parallel circuit. Voltage is the thing in a series circuit. And to solve these things is actually really pretty simple. The first thing we're going to do is we're going to trace the current out, right? And the first thing to do is to find the total resistance. And in a series circuit, it's very easy. The total resistance is just the total resistance. So this is 1 and 2 and 5 adds up to 8. Yeah? Okay. So step 1, add them up, right? 1 plus 2 plus 5 is 8 ohms, and the pressure is 24 volts, right? And so the next step is to find the one current, to rule them all, right? Okay. And so that's going to be, I'm using Ohm's law, I is V over R, right? So 24 divided by 8 Is that 3 amps? Yeah? Do we have that? Right? And so that is, we've now solved a lot of things, right? This ammeter is reading that same current. So it's 3 amps in that one, it's 3 amps this one. There's 3 amps going through there, 3 amps going through here, 3 amps going through there, 3 amps going through here, 3 amps returning to the battery. Yeah? It's like a little pump. 3 coulombs per second is being pumped around and around it goes. Yeah? Okay? Now, you might point out that there are like divergences here, like some current could go through this voltmeter, right? But our voltmeters are so good, we paid so much money for them that the resistance of these voltmeters is infinity. Now, of course, it can't be infinity, because if it is actually infinity, then no current could flow through it. Therefore, it couldn't measure anything because it wouldn't have anything to measure, right? So in reality, good voltmeters have resistances of 1,000,000 ohms, right? 1,000,000 ohms per voltage of scale. So, you know, it's like if it's on a 5-volt scale, it's 5,000,000 ohms, right? So that's the way this works. We're just going to assume that it's infinite, that no current actually goes through these voltmeters, that it just sits there and observes the pressure difference, right? And that's true, by the way, for pressure meters. Pressure meters, they measure actual pressure in water pipes, don't let water flow through them. They just let the water push on them, and then they've got some sort of sensor that measures how hard they're pushing, like a force gauge or something like that. Okay? Yeah? Current. I is current. Yeah. And V is voltage and R is our resistance, right? And then the final thing to do, pay very close attention. Okay? The final thing to do is to go and figure out the IR drop, the voltages across all of these other resistors. Okay? So if you look at this resistor here, this is, can we be quiet? This is 3 amps flowing through 1 ohm, so therefore the voltage must be, okay, that's not an actual pen. It sits there looking like a pen. This voltage on this guy, since V is IR, right? I'm just using Ohm's law, so that's voltage is current times resistance, right? 3 amps times 1 ohm is 3 amps, 1 ohm. What's that voltage? That's 3 volts, right? So this is 3 volts across this guy, right? The voltage across this guy, I'm just going to do I times R, right? So 2 ohms times 3 amps is 6 volts, right? And then on this one, it's 5 ohms times 3 amps, right? That's going to be 15 volts. And then if you look at this, this is all happy and good because we had 24 volts to drop. These wires are superconductors, so the pressure is not changing at all. Now a real wire, there really is a subtle change of voltage, right? Gets a little bit less, right? Okay, but these are superconductors. They're like a frictionless surface for the charge. You know, just there they go, right? So no voltage change, right? It's going through the ammeter. The ammeter has 0 resistance. Because if it had resistance, it would change the thing it's trying to measure. Does that make sense? So good ammeters have almost 0 resistance. Because otherwise, if they had a high resistance, when you plug them into the circuit, they would change the resistance of the circuit and change the circuit, and you couldn't measure it. Yeah? Okay? So this is, by the way, very alarming, because I'll have, every now and then you get a kid that goes, gee, I wonder how much current Portland General Electric provides. And they'll plug it into the wall. And you're basically plugging like just a dead short into the wall, because ammeters are designed to have very little resistance. And so the amount of current that flows, does anybody know the answer to that?
A lot.
No, there's a precise answer, fairly precise. In this room, it's probably 20 amps, right? And then something in the hall goes ka-chunk. There's these things called circuit breakers that are there just in case somebody plugs something into the wall that doesn't have any resistance, right? Otherwise, wires in the wall will glow red hot. And that's bad, right? Lights houses on fire. So there are circuit breakers that monitor the current in all the circuits. And if the current gets too high, they interrupt the current. Yeah. Yeah. You can blow a circuit breaker, yeah.